Cycle Wars, The Rise of Otto Cycles is an episode of the Degrees of Freedom project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. The previous video, Cycle Wars, The Power Awakens, introduced the equations used to model common air standard cycles and analyze the Carnot cycle. This video, Cycle Wars, The Rise of Otto Cycles, analyzes the Otto cycle, the diesel cycle, the Ericsson cycle, and the Stirling cycle, the Brayton cycle, and the turbojet engine cycle. As a review, here is the Carnot cycle on PV and TS diagrams, and plots of the efficiency as a function of the compression ratio and the pressure ratio. These are the bases of comparison for the other cycles. As a reminder, Q and W in this video are on a per mole basis. We'd call them intensive variables, but since they're not state variables, instead they're path variables. That terminology isn't used. It's worth noting that the real world is much more complex than models given here, but the models are very good for evaluating what happens as you change parameters in the real world. The numbers won't be precise, and a measured PV diagram will have rounded, not sharp corners on the transitions between the steps, but these models are very good for seeing trends. The Otto cycle is what is used to model the automobile, or gasoline-powered internal combustion engine. The steps are 1. An isentropic compression from C to D. 2. An isochoric heating from D to A. This step simulates the combustion. 3. An isentropic expansion from A to B. This is the power stroke. 4. An isochoric cooling from B to C. This step simulates the exhaust and intake step. For the Otto cycle, 2 steps, 1 and 3, have work transfer, but no heat transfer because they're isentropic, and 2 steps, 2 and 4, have heat transfer, but no work transfer because they're isochoric. The definition of thermal efficiency can be written as 1 minus the absolute value of Q cold over Q hot. For isochoric steps, Q equals C sub V delta T. Q hot is CV TA minus TD, and Q cold is CV TC minus TB. Plugging in, eta is 1 minus TC over TD, and just as for the Carnot engine, it's also equal to 1 minus R to the 1 minus gamma power. Because Q plus W equals delta U equals 0 for a cycle, the net work is negative Q hot plus Q cold, or CV TB plus TD minus TA plus TC. The effective compression ratio on the efficiency of an Otto engine is the same as for a Carnot engine. Race car engines have compression ratios up to 18 to 1, whereas passenger vehicles have compression ratios in the 8 to 1 to 12 to 1 range. The higher the compression ratio, the higher the octane rating of the fuel has to be to prevent pre-ignition or knocking. Prior to the 1970s, they used to add tetraethyl lead to increase the octane rating. In the 1970s, tetraethyl lead was outlawed, except for aviation fuel, to prevent the poisoning of the catalytic converters that were required to meet the new air pollution standards. The side effect is that humans also suffer much less lead poisoning now. Sometimes the unintended side effects are good. Many further details on the Otto cycle are available on Wikipedia. The diesel cycle is what is used to model the diesel fuel-powered internal combustion engine. The steps are 1. An isentropic compression from C to D. 2. An isobaric heating from D to A. This step simulates the combustion. 3. An isentropic expansion from A to B. This is the power stroke. 4. An isochoric cooling from B to C. This step simulates the exhaust and intake step. For a diesel engine, eta still equals 1 plus Q cold over Q hot after removing the absolute value signs. Q hot is now Cp TA minus Td, and Q cold is Cv Tc minus Tb. Note how Cp goes with the isobaric step and Cv with the isochoric step. Diesel engines have an expansion ratio in addition to a compression ratio. As listed, the expansion ratio is Vb over Va. The net work is negative Q hot plus Q cold, or Cp Td minus Ta plus Cv Tb minus Tc. Because of the expansion ratio complicating the math, the efficiency expressions are more complicated, but the graph shows the same trends as the Otto and Carnot engines. Diesel engines have compression ratios from 14 to 1 to 23 to 1 because the diesel engine counts on the high temperature compression to ignite the fuel, unlike the Otto where it's avoided at all costs. In the diesel, the fuel is injected directly into the cylinder at the peak of compression, unlike the Otto where the fuel and air are mixed outside the cylinder. Diesel engines are usually much more efficient than Otto engines, but they tend to generate a lot of toxic particulates. Check out Wikipedia for Volkswagen emissions scandal for further details. Again, Wikipedia has a lot more information on the diesel cycle. The Brayton cycle is what is used to model the gas turbine internal combustion engine. The steps are 1. An isentropic compression from A to B. This step simulates a compressor. 2. An isobaric heating from B to C. This step simulated the combustion. 3. An isentropic expansion from C to D. This simulates driving a turbine or expander. 4. An isobaric cooling from D to A. This step simulates the exhaust and intake step. The expression for eta hasn't changed, except for those pesky absolute value signs that keep appearing and disappearing. Q hot is Cp Tc minus Tb, and Q cold is Cp Td minus Ta, giving a net work of Cp Tb plus Td minus Ta plus Tc, and an efficiency of 1 minus the pressure, not compression, ratio, to the 1 minus gamma over gamma power. The terms of eta with RP are the same as for the Carnot engine. Gas turbine engines are used principally in power generation, marine propulsion, and in some industrial processes. They are currently banned from use in race cars, beginning with the IndyCar and Formula One car bans in 1970. Again, Wikipedia has a great deal of information on the Brayton cycle. The Brayton cycle with a regenerator is used to model a gas turbine internal combustion engine with a heat exchanger between the high-pressure gas and the exhaust gas. The steps are 1. An isentropic compression from A to B. This step simulates a compressor. 2. Isobaric heat exchange with the exhaust gas from B to X. 2a. An isobaric heating from X to C. This step simulated the combustion. 3. An isentropic expansion from C to D. This simulates a turbine or expander. 4. An isobaric heat exchange with the compressed gas from D to Y. 4a. An isobaric cooling from Y to A. This step simulates the exhaust and intake step. Q hot is added in the combustor, Cp times Tc minus Tx. The net work is W turbine plus W compressor. The turbine work is the change in enthalpy from C to D, Cp times Tc minus Td. For an ideal heat exchanger, Tx equals Td, so the efficiency is 1 plus Tb minus Ta over Tc minus Td. For low pressure ratios, the regenerator really increases the efficiency. For higher pressure ratios, not having regeneration is more efficient. The designer has to weigh both efficiency and complexity in designing a Brayton cycle with regeneration. The turbojet cycle is what is used to model the turbojet engine. The turbojet cycle is basically a modified Brayton cycle. The turbine creates just enough power to drive the compressor, and the still at high pressure exhaust is expanded through an isentropic nozzle to create high velocity exhaust that propels the jet forward. The steps are 1. An isentropic compression from A to B. This step simulates a compressor. 2. An isobaric heating from B to C. This step simulates the combustion. 3. An isentropic expansion from C to D. This simulates driving a turbine or expander. The turbine is set to generate just enough power to drive the compressor. 4. An isobaric nozzle expansion from D to E. This step simulates the exhaust nozzle on the jet engine. 5. An isobaric cooling from E to A. This step simulates the intake step. As stated, the work from steps 1 and 3 are equal but opposite, and Q hot is Cp Tc minus Tb. Td is calculated by setting Cp Tb minus Ta equal to Cp Tc minus Td. To calculate the nozzle, we do the first law, delta H hat plus delta of U squared over 2 equals 0. It can also be derived from the differential form, dH hat plus U du equals 0. Also, from a few videos ago, for an isentropic nozzle, V hat dP plus U du equals 0. Integrating the expression and recalling that PV hat to the gamma is a constant in an isentropic process, we get that UE squared minus UD squared equals 2 gamma P dV hat d, or using the ideal gas law, RTD over gamma minus 1 times 1 minus PE over PD to the gamma minus 1 over gamma power. The usual relationships among the temperature ratio, the volume ratio, and the pressure ratio for an isentropic process still apply. When performing these calculations, keep careful track of your units or you may not end up with velocities at the end. Wikipedia has a lot more information on turbojets. In turbofan engines, which are the most common type these days, more power is extracted by the turbine to drive large fan blades that drive air that bypasses the compression, combustion, and expansion stages, which increases the efficiency and quiets the engine substantially. Wikipedia also has much more information on turbofans. The Ericsson and Stirling cycle engines are external combustion engines, meaning that the heat is applied from outside the engine to the working fluid. The heat doesn't have to come from combustion, but often does. The Ericsson cycle steps are 1. An isothermal compression from A to B at temperature T1. 2. An isobaric heating from B to C at pressure P2. 3. An isothermal expansion from C to D at temperature T3. 4. An isobaric cooling from D to A at pressure P4. Because there are no isentropic or isochoric steps, heat and work must be accounted for in each step. For isothermal steps, delta U and delta H are 0, so the work and heat are equal but opposite and calculated as RT times the log of the pressure ratio. For the isobaric steps, the heat transferred is C sub P delta T, and the work is P delta V hat. After much algebra, the net work is minus R T3 minus T1 times the log of P2 over P4. Q hot is Cp T1 minus T3 plus R T3 log of P2 over P4. The efficiency is as given. Note that Q2 equals negative Q4. So if we could use a perfect heat exchanger, we could recover the heat from step 4 and use it to provide the heat for step 2. With this change, Q hot becomes R T3 log of P2 over P4, and the efficiency becomes the Carnot efficiency. There are many engineering challenges in doing so, but the increased efficiency makes the Ericsson cycle tempting to implement. However, it has found little to no commercial applications. Again, Wikipedia is a fruitful site for finding additional information. The Stirling cycle is similar to the Ericsson cycle, but replaces the isobaric steps with isochoric steps. The Stirling cycle steps are 1. An isothermal compression from A to B at temperature T1. 2. An isochoric heating from B to C. 3. An isothermal expansion from C to D at temperature T3. 4. An isochoric cooling from D to A. There is no work consumed or generated in the isochoric steps, so the net work is negative R, T3 minus T1, log PB over PA. Q-hot includes both steps 2 and step 3, so it equals CV T3 minus T1 plus R T3 log of PB over PA. Since Q4 is equal and opposite to Q2, if we had perfect heat exchange between step 2 and step 4, the efficiency again reduces to the Carnot efficiency. Unlike the Ericsson engine, the Stirling engine finds wide commercial use. By numbers of units sold, the biggest use is as little demonstration or hobby units, as a quick search of web-based sales sites will reveal. They are also found in cryocoolers, remote power generation, and waste heat recovery. As with the Ericsson cycle, Wikipedia is a fruitful site for finding additional information. Again, thermodynamic models in Cycle Wars, The Power Awakens, and the rise of Otto cycles are not the only models you need to design engines, but they do function well for establishing trends and estimating power output early in the design cycle. However, full engine design requires material science and engineering, strength of materials, kinematics, heat transfer, fluid flow, combustion kinetics, and process control at a minimum. The takeaways from this video are: 1. The Otto cycle is a thermodynamic model for the internal combustion automobile engine. 2. The diesel cycle is a thermodynamic model for the internal combustion diesel engine. 3. The Brayton cycle is a thermodynamic model for the internal combustion gas turbine engine. 4. The turbojet cycle is a thermodynamic model for the internal combustion turbojet engine. 5. The Ericsson and Stirling cycles have not found wide commercialization, but hold promise for high thermal efficiency. Thanks for watching. This video is brought to you by the DOFPro team.